For the rest of the semester, I will talk about the deadlocks, which is the next chapter. So I won't have time for looking at security and the details of Windows. Those two chapters were the chapters that I wanted to cover actually. So it is up to you to read those chapters because they contain some very important information. But as I said, I won't have time to cover. What is it? 51. Okay. Those topics. So the clock is considered as an I/O device. Actually, it doesn't do much. It is very different from the other I/O devices, as the book mentions a few times. But still, we study them under this name, under this chapter of I/O.
Tamam. Great.
Okay. So there are two types of clock hardware. The first one is a very old way of doing it. You know that the alternating current is doing this, right? This is the alternating current. Our regular power grid uses this 220 volt alternating current to deliver power to our homes and computers. So they used to trigger a clock tick at the zero cross of these waves. So the clock was free for the computer. It didn't have any hardware. It was just using the regular power to drive the clock. But nowadays nobody is using these because these are very old and you cannot play with them. You depend on the power source. And with the laptops and all kinds of newer type of computers, you don't have the power source actually. Most of the time you run on the batteries. So that's why they don't use these. So the other kind of clock has three components: a crystal oscillator, a counter, and a holding register, like this. This is the crystal oscillator. Okay, you put a crystal, some kind of a physical material, okay, under some tension, and you apply some current to it, and it starts oscillating. So it produces a waveform like that, okay. And depending on the tension and the crystal type, you can adjust the period of this signal. And there is a special circuitry at the peak of each tick, okay. It increments this counter by 1. So when this or decrements the counter by 1, the counter is decremented. Sometimes incremented, but most of them it is decremented. You decrement this counter by 1. This is called the counter. When this counter reaches 0, okay, it produces an interrupt. Okay, it produces an interrupt. Says that okay, I am done counting, and it produces an interrupt. Then you copy the contents of this counter into this holder again, and the whole process starts from the beginning. So at regular intervals, you receive a timer interrupt from your clock hardware, and it is up to you what you do. It is up to your operating system what to do about this interrupt. So that's the main idea for the clock hardware. It is a very simple hardware, much simpler than disks or network cards or the graphics cards and that kind of stuff. It is very simple. All it does is produce an interrupt at given time intervals, maybe every 10 milliseconds, or maybe every millisecond. You produce an interrupt depending on your hardware operating system needs. Okay. So the signal is fed into the counter to make it count down to 0. When the counter gets to 0, then it causes a CPU interrupt, and you handle that interrupt. Okay, so this is the hardware that is used most of the time. We will not talk much about the hardware because that's it. That's the clock hardware. We will talk about mostly about the clock software. Okay. So I talked about this last time at the end of the class, but I was in a little hurry, so I was rushing. So let's go back and talk about them one by one. These are the 6 duties for a clock driver. Okay. Since this is the hardware, there is a driver on top of it using this hardware, and these are the tasks of the hardware. Maintaining the time of the day. We need the time of the day because we need to put that information into the files when you create them, when you modify them. Okay, that kind of stuff. Second one, we use it for the preemption. What do I mean by preemption? If a process is running too much, if it is taking too much CPU time, then you need to stop that process and let the other process run. So how are you going to measure that time, how much time it used? It's called preemption, and the clock is used for that one. Also, how much a process is using the CPU is measured by the clock. Handling alarm systems from user processes, we will talk about this. There are very interesting issues about this one. Watchdog timers, again, another interesting technique for the operating systems to keep them stable. It uses the clocks, and then we have the monitoring and profiling and statistic gathering. Let's talk about them each one by one. Maintaining time of day is important. So it requires incrementing a counter at each clock tick, as mentioned before. When the clock ticks, you increment your counter. So let's say you have a 32 bits of counter that counts the number of seconds. Okay, number of seconds. So you can measure 2 to the power 32 seconds from the time where you are measuring your time. In Unix system, it is January 1st, 1970. Okay, this integer counts the number of seconds from January 1st, 1970. But if you are counting the seconds, that's fine. But if you are counting the interrupts, and if you are interrupting your CPU 60 times a second, then your 32-bit counter will just overflow in 2 years. Okay, so this is not good. So if you are counting the number of interrupts, and if you are getting a 60 times an interrupt a second, then this place will not be sufficient for you. Either you need a larger space or some other solution. You could use 64 bits of integer to count your text, that is the number of interrupts. But in this case, 64 bits is some computers, they don't have this kind of a word. It might take time to update two 32 bits for each interrupt. So some people don't prefer this one. Another solution, the second solution would be this. Use 32 bits for the seconds. Okay. So within the second, you keep the number of ticks in a separate byte or in a separate integer. Okay. So it is 32 bits for the time of the day in seconds, and another integer that keeps the ticks within the second. Remember, this one is being decremented by 1 from each oscillator tick, and this number, when it reaches 0, an interrupt is formed, is created. How many times an interrupt is created depends on your operating system needs. So how many times this interrupt is created within a second is stored inside this integer. So it could be maybe maybe 1,000 times a second. So that means that every 1 millisecond you have an interrupt. So you need to have large enough place to keep that data. Once this data reaches the maximum in a second, then you increment one of these. Okay. Another solution is keep two 32-bit integers. One counts the ticks, okay, and the other one counts the system boot time in seconds. Okay. So this is the system boot time, and this is the counter of the ticks after the boot time. So if you are not using your computer for 2 years, okay, if you are not using your computer for 2 years without rebooting, this solution might work. Okay, so these are the three solutions used for. These are the three solutions used for keeping the time of the day within your computer. So your computer has a clock, and at each clock tick, you are decrementing this counter. This counter reaches 0, you produce an interrupt. After that interrupt, what you do is, increment one of these counters depending on your solution. Okay, any questions? So this is how you keep the time of the day with your computer, and that's one of the tasks of the clock driver. The second task of the clock driver is preventing processes from running longer than allowed. Okay, whenever you create a process, whenever you start a process, your process scheduler, it initiates a counter to a value that process is quantum in clock ticks. Remember, we had the quantum times for each process, and we initialize that number in clock ticks, not in seconds, not in milliseconds, but in clock ticks. So at every interrupt, clock driver decrements the quantum counter by 1. When it gets 0, the clock driver calls the scheduler to set up another process. So this is how it works. We always mention that when the time passes long enough, then you interrupt your process and you switch to some other process. That's what we were saying, but this is what is happening actually. So every let's say 10 milliseconds, you are having an interrupt. Each interrupt, you decrement this quantum number by 1. When that number reaches 0, that means that your process is done using the CPU. You schedule another process to run. So this is the second task of the driver, to keep processes from running the CPU all the time. So this is the second one. Third one is the accounting for the CPU usage. How much my processes are using the CPU is an important issue. You would start a second timer. I mean, in your computer, you don't have to run only a single timer, a single clock. You might have many of them. So you might start the second timer whenever a process is started up. When that process is stopped, the timer can be read out to tell the CPU usage. So for each CPU started, for each process using the CPU, you start a timer. When the process stops, you read that timer and you put that information inside the process table of that process table entry of that process. Okay, so this requires a second timer. Okay, a simpler way. Okay, less accurate but simpler. It doesn't need any counting any second timers. Okay, okay. You maintain a pointer to the process table entry for the currently running process in a global variable. Okay, a global variable keeps the pointer to the process table entry of the current process. Okay, at every clock tick, because clock tick is already happening. Okay, a field in the current process entry is incremented. That's it. Okay, so you are not keeping the exact time, but you are using the time in terms of ticks, clock ticks. Okay, and the clock is incremented when there is a CPU interrupt. So this way, every clock tick is charged to the process running at the time of the tick. So this is less accurate because it is not measuring the exact time. and your process may not use the whole interrupt time, so that's the less accuracy part, but it is much simpler than the previous solution, which requires starting a new timer every time a process uses the CPU. So this is accounting for the CPU usage. This is the third task for the clock driver. Let's look at the next one, handling the alarm system call from user processes. I mean, interrupts occur at every interrupts occur because there is an I/O event, or there are regular interrupts. At every clock tick, there is an interrupt occurring. Sometimes the users might want to produce the interrupts. Okay, the user says that produce an interrupt. Okay, produce an interrupt in, let's say, 20 milliseconds, so that I can do something. This is one example. One example is package transfers in networking. Let's say you transfer the package, you put the destination, okay, you send it to somewhere, and you set up an interrupt, say that timer that says that wake me up in 200 milliseconds. Why you are saying that? Because you are saying that because if in 200 milliseconds, if you don't receive an acknowledgement, if you don't receive the news from the other side that says that your package is received, then you need to resend your package, okay? Because your package might be lost, right? So you ask the operating system to produce an interrupt, okay, in 200 milliseconds, so that in 200 milliseconds you can check if the acknowledgement is received. If it is not received, then you are going to send it again. This is called timer, and the users are alarm system call from the user. Users are using this for this kind of tasks, the time-dependent task. The operating system handles the time counting for you. Okay. So how is this done? One way is to maintain a table in which the signal time for all pending timers is kept. So there is a table. Each process puts the timer request in that table. Okay. And whenever the operating system checks that table, whenever the time comes, it just produces an interrupt, or it just wakes up that process waiting for the timer. Whenever the time of the day is updated, the driver checks to see if the closest signal has occurred. If it has, the table is searched for the next one to occur. So the structure is like this actually. Let's say this is our current time, okay, and this is our table, like a linked list. Okay, one process says that, okay, wake me up at this time. The other one says that wake me up at this time, and this time, and this time, and this one. So there are 1, 2, 3, 4, 5 processes are waiting to be signaled. Okay, so they say that signal me when the time is up. Okay, so this is the current time. So the clock hardware, whenever the time is updated, okay, time of the day is updated, the driver checks to see if the closest signal has occurred. The driver comes here and looks at this one, okay. It says next signal is in 3, okay. This is how much time before I wake up or signal a process, okay. So it checks this one, 3. So I need 3 more interrupts, 3 more clock ticks. So it makes it 2, okay. And then next time the time is updated, it makes it 1, and it is 0. When it is 0, then it wakes up whoever issued this signal. Okay. Then all the rest of the fields are updated, so that we would know when they will be waken up. So this is how do we keep these system alarm times. You keep them in a table or in a linked list, and there is the current time, I know this one, and there is the next signal, I know this one. This number is decremented every time the clock is updated, And when this number reaches 0, you wake up the process that issued this call and you update all of these. And you put the number, the next number, here. That is the number 4. And instead of 0 after that, it is number 4. And you continue that way. Okay? When number 4 is done, then you remove it, you put the number 6 in here and continue that way. Okay? Yes?
3 kaldırdıktan sonra 4 değil 1 oluyor.
No, so these are the numbers, okay? One process says that 4203 is when I am going to be signaled. This one says that 4207. So it is 3 plus 4 plus 6 plus 2 plus 1. Okay? So, no, okay, so I understand your question. I made a mistake, sorry. I said that you update all these numbers. No, you don't update all these numbers. That's what I said, right? So, when this number reaches, okay, let me start from the beginning. Okay, I made a mistake, sorry. So that confused you. I said that, okay. So, whenever the time is updated, okay, you come to this number and you decrement it by 1. Okay, it is 1, 2, then 1, then 0. When it reaches 0, okay, you signal this the process that issued this signal, okay, and you put this number 4 here. So it is number 4. Okay. So the 4 goes to 310, and you put that number 6 there, and continue that way. Continue that way until all of the signals are done. Whenever a new signal request comes, let's say, wake me up at 4210. So what you are gonna do, 4210. You need to put that number. This is 3, okay, and here, right? It should be 7 and 3. Yes, there should be a lane.